Okay, so last time I could have defined this PIT problem. I talked about hitting sets and generators and sort of solution concepts for PIT. At the last 10 minutes or so, I mumbled some incoherent words about harness versus randomness. The punchline I want you to take away from that is that, to some extent, we can't expect efficient deterministic algorithms for PIT for models of computation which we cannot prove lower bounds. Because if we had, such PIT, we would get lower bounds. So it sort of makes sense to get lower bounds first. Given that, I want to talk about PIT where lower bounds are known and see how we can stare at those lower bounds and get identity testing out of them. Okay, so there's two models of computation I want to talk about. They're both very, very simple. The lower bounds are, we either saw them this morning or sort of easy, but the PIT takes some additional further ideas. So one is sparse polynomials, which I'll define, and the other is depth powering, which we already saw, but I will define again. Okay, so let's talk about sparse polynomials. Okay, so basically, sparse polynomial is like, usually, again, it's going to be n-variate degree d, right? There's some number of monomials, n plus d choose d possible monomials. We're going to say it's sparse if only a few of them are non-zero. Okay, so you have a polynomial like this, right? This is the way I'm writing my coefficients, but I'm not going to iterate over all exponents a. I'm just going to have something from a summation from I from 1 to s, and the number of exponent vectors I'm going to have is just s of s exponents. Okay, so this is going to be something called s sparse. So when I write it this way, it's very clear there can be at most s non-zero coefficients to this polynomial, and these are sort of pretty simple things. Okay, so right, I drew the circle of life, right? Let's start with lower bounds, right? Can we get lower bounds for sparsity? Right, this is sort of trivial in the sense that things like the determinant or much simpler polynomials are very non-sparse. They're exponentially non-sparse, but yet they can be computed efficiently. So lower bounds, it's sort of like, learn it in middle school or something. I don't know. Yeah. Okay, but what about like white box PIT? Right, I give you an expression of this form. You want to decide whether it's 0 or not. Okay, this is also very simple because I give you this expression, and I'm only giving you s of these alphas. Right, you just check whether any of them are non-zero or not. So okay, so white box is still also very, very simple. The challenge here is, what about black box PIT? Can we get hitting sets for this class of computation? Okay, so sparse polynomials are fairly natural in a lot of areas. You actually, if you Google sparse polynomials, you get however many hits, and they occur a lot of places. But I want to motivate this, particularly in reference to what was discussed in the morning about depth. Okay, so I want to say that PIT for sparse polynomials is in some sense equivalent to PIT for depth 2 formulas. Okay, so for some people who have seen this, it might seem, oh, of course, this is extremely obvious, but there is one subtlety. Okay, and what is this? The subtlety is, what is a depth 2 formula? Well, there are basically two possibilities, right? So if there's depth 2, you have your top gate, you have some layer of gates, and then you have your things at the bottom. We can assume that the gates are alternating, because if you have addition, right, you can sort of like, if you have an addition gate like something like this, you can collapse them to something like this, where you just sort of shortcut all of the edges. Okay, so we can assume that they're alternating, and basically now there's two steps, two cases, right? Either you have an addition gate at the top, and then you have multiplication gates, something like this, or you have a multiplication gate at the top, and then you have addition gates at the bottom. Okay, there are two cases. I want to say the first case is exactly a sparse polynomial. Okay, so this should be relatively clear in the sense that this fan-in is something small because that's bounded by the size of the circuit. Each of these things, this is a multiplication. What you have down here is either going to be scalars or variables. So the product of that is going to be a monomial. And then you take a summation. It's a summation of monomials. It's sparse. Okay. Over here, what do you have? You have a product over a sum of things. And what are you going to have here? You're going to have either input variables or scalars. So it's going to be a linear form. So here you're going to have products of linear forms, or degree 1 polynomials or whatever. Okay, which also happen to be sparse. But the reason that I'm saying this is because, recall, in the last lecture, I defined a generator, which says that if you can get a PIT for one class, you can also get for products. Right? So this is saying that if you get a generator for sparse polynomials, which includes linear polynomials, because linear polynomials are sparse, then you can also hit products. So it's saying if you get PIT for sparse, you get PIT for general depth 2. Okay, so this is basically saying that from the perspective of PIT, it's most interesting to have a computation where the top is an addition gate. If you have a multiplication gate, you can just sort of pass to the factors and use a generator, and you're fine. So with that comment aside, I just want to then dive into the result I want to talk about, which is that there's efficient explicit hitting sets for sparse polynomials. And there's like a variety of ways of doing this. I am vaguely not going to follow, but kind of following this paper of Klivans-Spielman from 2001. And what are they saying is that there's a polynomial in S and in D size, explicit hitting set for S sparse polynomials. Okay. So what is the proof idea here? Well, it's basically the following. We have n variables, okay? And as I sort of said last time, if you have a generator takes n variables to L, and if L is really, really small, then we can brute force, right? In particular, if L is 1, we can use a univariate hitting set. We just go one pass to the degree bound, okay? So basically, we want to reduce from n variables to 1, okay? Okay, and obviously, I need to use the fact that this is a sparse polynomial to make this work, because otherwise, I would have done PIT of everything, and I would get a Gödel prize or something. But basically, the way I want to do this is I want to do this sort of without collisions. And I want to make that precise in some sense, in the sense that sparse polynomials have something combinatorial about them, and there's something like hashing. And when you have balls in the bins, balls can collide. Okay, and I want to do that without any collisions. So what do I really want here? So I want a map phi. It's going to take a tuple of natural numbers, and it's going to give me 1. And I want it such that, so my sparse polynomial here, right, it's going to have a bunch of exponent vectors, a1 to as. And I want that phi on a1 up to phi on as, I want these, this is going to take an n tuple, it's going to give me a number, right? I want these numbers to be distinct. Okay, and that's what I mean by there's no collisions. I'm going to have a map which takes n variables down to 1, and I want to make sure that when I apply it to these S exponent vectors, there are going to be no collisions at all. Okay, so let's see why this is helpful. And my notes will tell me why. Okay, right, so you have F, which is alpha AI, x to the AI. And what is this going to get mapped to? Right, it's going to get mapped to what you would expect. Where now what I'm going to do is I'm going to replace these n variables here with a single variable. I'm going to call it y. And the exponent is phi of the appropriate exponent vector. And the point is that if all of these are distinct, I want to say that this univariate polynomial is non-zero. Why is it non-zero? Well, basically, I have a sum of monomials, and they all have different powers, right? So they can't cancel them out if this initial thing was already non-zero, which is what we're assuming to be the case. Okay, so I go from n variables down to 1, right? And then I need to interpolate. So let's call this, I don't know, f tilde of y. Interpolate f tilde at y at degree of f tilde y plus 1 points, right? Because this is a non-zero polynomial, then I want to get a non-zero evaluation of this polynomial. That's my hitting set. Okay. Yeah. Okay. Yeah. But if you interpolate, yeah. I mean, but the reason yeah, that's not really an important difference. Okay. So this would be great if you could do it, but you can't. And the reason for this is because the way I phrased it is I wanted one map. Okay. And the thing is that if you only want one map, then this degree cannot be small. Okay. So there's sort of an inherent tension between the degree that you're going to get and the number of maps. Okay. And so what we're going to do is to actually get a small degree, we're not just going to use one map, we're going to use a family of maps. Okay, so I'm going to have capital phi is a collection of maps, and I want that there's some phi in big phi where this is true. Okay, and I'm going to allow a collection of maps, and that way I can get a low degree. Okay, so what do we really want? We want, first of all, that the collection of maps is small. We also want that the degree of f tilde is small. Okay, and these are competing constraints. But If I just told you this, you might go to randomized algorithms and look at balls and bins and say, pairwise independence, I'm done, or something like this. The challenge here is that we live in algebra land. And so this map phi needs to be algebraically natural. Okay, so these maps need to be algebraically compatible with this black box PIT problem. In the sense that what I did here is I just sort of said, well, we're magically somehow replacing these exponent vectors with phi of the exponent vector, right? But I don't give you the exponent vectors. All I'm giving you is evaluation access to this polynomial. You need to be able to somehow massage your inputs to induce this map. Okay, so you can't just use anything here. You need something that's compatible with the problem at hand. Thankfully, you can do it, which is why I'm giving this talk. Okay, so let's start though with the flawed idea of just using one map and see what happens. Okay, so this is something which is pretty well known. It's something called a Kronecker substitution. Predates my birth by 100 years, which is the following. Okay, it's going to be a map, say, called psi sub d. And what's going to happen? It's going to take f of x, and it's going to map it to a single variable. So it's going to be f on y. And yeah. Okay, so there are n variables here, one variable here. And how is this map going to work? It's going to just define on each variable xi is going to map it to y to the d plus 1 to the I. Okay, so d is a parameter here. It also happens to be the degree of the polynomial that I'm considering, which is not a coincidence. We're just going to take this x and map it to this really, really large power of y. Okay. And this is the map, this is the definition. And the claim here is that this map is injective on not the entire ring of polynomials, but those polynomials and n variables which are of degree at most d, which are the ones that I care about. Okay, so no matter where you start with here, you map it here, you're going to get a univariate polynomial, and it's always going to be injective. Okay, in particular, it's going to preserve non-zeroness. Okay, and what's the proof of this? It's basically the uniqueness of base, d plus 1 expansions, right? So we all know that base 10 expansion of numbers are unique. Base 2, this is just base d plus 1, right? Because if you take a monomial x to the a, what's going to happen? You're going to get, a1 is going to map to a1 times d plus 1, right? And so on. So you have a monomial x to the a. It's going to map to y to some power. It's going to be a1 times d plus 1 plus a2 times d plus 2 squared, d plus 1 squared, plus dot dot dot, an d plus 1 to the n. Okay, so this is some number. Each of these AIs are at most d, because I'm assuming that this is a low degree monomial, and this uniquely this is unique on monomials, and then you can pass to uniqueness on polynomials in the entire ring. Okay, so this is a single map, which is injective on this entire thing. In particular, it's injective on sparse polynomials. So this does satisfy what I wanted here, right? But the challenge is, what about this degree, right? If you look at this map, you see that you can have a monomial. It maps to degrees, monomials in y, which are of exponential degree, which is bad because if you wanted to then interpolate, you'd get exponentially many points, and that's sort of useless. In particular, I didn't ever use the fact that I started with a sparse polynomial. This is injective on this entire ring, which is like really huge. Right? So we need to use sparsity in some way. And so what we're going to do now is just use conventional ideas from hashing, which is that we're going to work modulo a random prime. Okay, so go modulo, go mod p. All right, so what's the lemma here? Is suppose you have m1 up to ms. Right, so these are sort of the numbers I'm getting from this Kronecker substitution. And these are going to lie in some range, 1 up to n, capital N. N is going to be really big. What I want to say is that there are at most some number, which I'll leave blank for now, primes p, such that what? If you take this all of these things, you go mod p, we want to say, is it distinct mod p? So look at this set, or multi-set, m1 mod p up to ms mod p. I want this set to be distinct. okay, all of these things be distinct, and I want to say that, you know, some primes are going to be bad, but I want to say that most of them are good, and so how many of them are bad? And it's going to be s squared log n. Okay. So let's go ahead and prove that. Well, you know, how can elements in the set not be distinct? Well, certainly if there's any two of them are the same, right? So let's look at, you know, si minus, or mi minus mj. Let's look at the primes that divide this particular, so p such that p divides this quantity, right? This quantity is of absolute value at most n. Okay, so this is some number at most n. How many primes can divide this number? Well, every prime is at least 2, right? So there can be at most log n primes that divide this. So this set is of size at most log n. Right, so there are most log n primes for this particular difference, right? And how many differences are there? There's s squared differences, right? So there's at most s squared log n primes where one of the differences are the same modulo that prime. Okay, so that gives you what you want. Great. Okay. Now the unfortunate thing about this is that you need to know some things about the primes, right? And it's not really that hard. But you know, here's this lemma or fact or whatever that the nth prime is at most order n log n, right? So like this is like a very weak version of the prime number theorem, but you sort of need to make this work because if the nth prime was really, really big, then this would be bad. Like you need to search for many, many primes. But the point here is that the primes you're working with this will be polynomial in all the parameters, so you don't even need things like AKS efficient primality testing. You can just sort of brute force over everything, and it's all fine. Okay, so let's put this together. So what's the corollary here? Is that suppose that you have f, right? This is our sparse polynomial. You have alpha a sub I x to the ai, right? And we're assuming it's non-zero because that's what we want to hit, right? Then there exists some p, which is order O tilde s squared n log d, right? So it's n variate degree d, and its sparsity is s. There's some prime, which is at most of this, which is polynomial in all the relevant parameters, such that what? If we do the Kronecker substitution modulo p, there's no collisions. Okay, so there exists a prime of this size, such that if you look at the univariate polynomial f, where you plug in the following, you have d plus 1 mod p, that's the first variable. The second variable, you plug in d plus 1 squared mod p up to y to the d to the 1, d plus 1 to the n mod p. Okay, so this is a y is one variable. In each of these coordinates, you're having some power of y modulo p. So everything here is going to be a degree at most p in all of the coordinates. I mean, it seems really large, right? You have d plus 1 to the n. It's a very large number, but you can compute this efficiently via repeated squaring. So this should not be scary at all. Okay, so you started with a sparse polynomial on n variables, and there is some small prime such that this univariate polynomial is also non-zero, right? And so that implies that the hitting set, the following thing is a hitting set, right? This is a univariate polynomial. We just need to now plug in a bunch of points, do interpolation or evaluation or whatever, right? So what points are we going to use? Well, we're just going to take replace y with a bunch of evaluations, right? So we have alpha to the d plus 1 mod p up to alpha to the d plus 1 to the n mod p, where the alpha is from some set. And like how big of a set do we need to choose? Well, we just need to choose the size of the set to be at least what? Well, f is a degree d polynomial. We're plugging in things which are of degree at most p, right? So s should definitely be bigger than something like p times d. But notice p is something like this. So really, we can say s is some polynomially larger than s, d, and n. Okay, so this is our hitting set. And I want to say, so first of all, see, and I haven't proven correctness yet, or it's sort of obvious, but let's see that it's, it's small, right? This set is small. The number of primes is also small. So this is, H is poly-sized. Okay? And sort of how does the correctness go? Well, I guess it's sort of obvious at this point, right? Basically, you take this polynomial here, you do the Kronecker substitution, it preserves everything. There's no collisions. You find some prime where there's no collisions, right? And basically none of these things can collide, so you can't induce zeroness, and then you just interpolate, and you're done. Right. Okay, so this is PIT for sparse polynomials. It's a polynomial in the sparsity and the number of variables and the degree and so on. I think you can do this is sort of like s to the fourth. I think you can do slightly better using other methods, but that's not super important here. Okay. So sparse polynomials in general are very simple. As we sort of saw, lower bounds are simple. Identity testing is very simple. White box identity testing. Now I want to do something which is slightly less trivial, but still not too hard. Okay, so let's talk about depth 3 powering formulas. So Ankit talked about them in the morning. Yeah. Yes. Right. Okay, so Pratisha's question is, I said that for depth 2, sparse suffices. That basically, if you have a generator for some class C, then you have a generator for C times C. But the problem is that if you have a generator for C, it doesn't mean that you have a generator for C plus C. And that's what, and to go from depth 2 to depth 3, you need to have a summation gate. Yeah, if you had a depth 3 with a product gate at the top, then that's a product of sparse polynomials, and so you could also do that. But yeah, the challenging thing for depth 3 is when the addition gate is at the top, which is a whole other beast. This thing. No. We know nothing. So there's actually a conjecture of Agarwal. I'm not sure if he stands by it at the moment or not, but there's some conjecture of Agarwal that basically says that this generator works for any constant depth. But that was made 10 years ago or something, and I'm willing to let that slide because things have changed. I don't know. Yeah, but there are.
But I thought for depth 4 is the same thing as if you get PIT for depth 4, you get it for general circuits.
So if you get polynomial size PIT, polynomial size hitting sets for depth 4, then you get quasi-polynomial size hitting sets for general circuits. Yeah, to some extent, that's why I'm willing to let it slide in terms of the original conjecture. But I think the original conjecture, I'm not sure if it was polynomial size hitting sets or it might have been quasi-polynomial size hitting sets. The thing is, if you get quasi-polynomial size hitting sets for depth 4, I don't think you get anything non-trivial for general circuits. So it's a very subtle balance. Right, in the same way that we have lower bounds for depth 4 of 2 to the root d or something. But yeah, the same issue. Okay. Okay, so Ankit defined depth, sort of talked about depth 3 powering circuits. I think Ramprasad defined it. I'm going to do it again, because I'm not going to assume anything. Okay, so what was the definition here? Okay, so this seems like a little bit less natural, but I want to remind you why you saw it before and why that was natural. Okay, so it's going to be a summation of powers of linear forms. Okay, so you have a summation 1 to s, and then you're going to have a linear polynomial in, just running out of room here. Okay, so you have a summation gate here. This is a linear polynomial in x's. Okay, so the alphas are coefficients. I'm not necessarily assuming this is homogeneous, so there's this free term here, this constant. And then you have linear in x1, linear in xn, and then you have some power, which is horribly typeset, which is some exponent d here. Okay, and based on, I'm going to make the assumption, you don't really need to do this, but I'm going to make the assumption that actually all of the exponents are at most d. Not just that the polynomial itself is at most d, but the exponents. You don't need to make that, but I'm going to do it. Okay, so this is the model we wanted to consider. And just to remind you sort of why we discussed this, Ankit used this in this reduction at depth 3, going from depth 4 to depth 3. Ramprasad talked about it in terms of this partial derivative method. It's a very nice test bed for a lot of methodologies. And then I'll discuss some more motivation briefly. But I just want to say one thing in terms of notation. Right. So again, there's a summation gate at the top, since for PIT that's sort of the most interesting thing. But there are also other gates, and the way I want to write this conveniently is, as a notation, is the following. So there's a summation gate here. This corresponds to this guy. And there's an S saying that the fan-in of this top gate is S. This is a powering gate. It's supposed to be like a caret on your computer. Okay, it's exponentiation. The fan-in here is at most D in the sense that you're taking this linear form to some exponent. And this is the summation corresponding to this form. This is the notation I want to use. And what is the size of this thing? The size is going to be S times D plus 1. There are other ways of defining it. I'm just defining it this way. So there's the top fan-in, and then there's D plus 1. Okay. So what did Ramprasad prove this morning? Right? Because the idea that this is some model. If you want to do PIT, you first better do lower bounds. Let me remind you what Ramprasad did, is that if you have the monomial x1, xn, it requires 2 to the omega n size as a depth 3 powering formula. Okay. So this is saying, this is a very simple polynomial, and yet it cannot be computed efficiently at all in this model. So this is saying, these are like embarrassingly weak, in the same way that sparse polynomials are embarrassingly weak. But somehow, this still remains a challenging problem to do identity testing. Okay, so let me tell you what is known about this in terms of identity testing. Okay, so works of Shpilka and Saxena in 2008 gave a polynomial time white box. Okay, so we have great lower bounds and we have polynomial time white box. Black box is more elusive, so let me tell you vaguely some results here. There's this work of ASS. Markers, yeah. That's not going to work. Okay. There's work of ASS in 13. There's work of myself and Amir in 13A and then 13B. So there's these 3 different works using different methods, and they all show a polynomial in S to the log S size hitting set. So I'm sorry, I'm not going to be able to fix this. I'm going to use S for size and also the top fan-in. That's an abusive notation. Consider yourselves abused. Okay. Okay, so these 3 different methods, they all give you polynomial in log S size hitting sets. So it's quasi-polynomial. And then there's this work of myself, Ramprasad, and Amir, which gives polynomial into the log S size hitting sets. Okay, so the best that we know so far is polynomial to log S, and I think an intriguing open question is just to get polynomial in S hitting set. Okay, so this is a very embarrassingly simple model. We can't compute anything really of interest, and yet somehow we still can't get hitting sets, which I think demonstrates the idea that you really need to stare at low bounds until your eyes bleed to actually make these things work. Okay, so what I want to do now, when do I have till? I don't remember. Sorry, 4? Okay. Okay, great. Okay, so what I want to do now is I want to review the lower bound technique to show this theorem. Okay, then I want all of our eyes to bleed to see the work that needs to go to get this poly to log S size hitting set. So there are 3 different techniques here. I'm going to describe this one. Okay, in the next lecture I'm going to describe this one, and tomorrow I'm going to describe this one. Okay. And they all have their different merits, and they do different things. This one is specifically for this class, so that's why I'm doing it now. Okay. Okay, so how we do the proof? Right. So following the philosophy of this morning, we want to use a complexity measure. Right. We want to find some mu which has these nice properties of subadditivity, and you have building blocks and whatever. And I'm going to do it slightly different than Ramprasad did it. And I have slightly different notation and everything. So what is this? I want to say this is going to be the space of all partial derivatives. So Ramprasad this morning only looked at partial derivatives of order k. I want to do everything. It's not really that different, but okay. So I want to consider all partial derivatives of your polynomial f. Okay, and so to clarify notation, what I mean by this is in more familiar calculus notation, the following differential operator. You're differentiating x1 to a1 times and xn an times, and then there's like this weird notation or whatever. Okay, so you're basically taking all partial derivatives. Okay, so this is an exponentially large set. Okay, so there's many partial derivatives, but the whole point of this complexity measure perspective is to say we can measure this set in a more refined way using linear algebra, right? Because this is contained in this, it's in the space of all polynomials, right? This itself is an F vector space, right? So we can measure this set with dimension, and that will actually be our complexity measure. Okay, so mu will be the dimension of mu of f will be just the dimension of the space of all partial derivatives of f. Okay, so Ramprasad had a very explicit way of looking at this thing as the rank of a particular matrix.
Can I ask one question?
Absolutely.
So in that, the top theorem, you would say that
This one. Yeah. Yeah.
you would say that it requires that much size even to approximate it infinitesimally closely, because it's there are close conditions.
Yes.
But in the black box, whatever your for is the log is size setting, that is not for infinitesimally. That doesn't work. There's something breaks down, right?
No, it's fine. I mean, at least these are fine. This I need to think about. This should be fine. I think they're all fine.
Even for infinitesimally close approximation. So maybe you should show me exactly.
Yeah, we can talk about it offline. Yeah. Okay. Yeah, so Katan asked questions about an alternate model of computation where you involve things like limits. I will be talking about that on Sunday, Tuesday, I don't remember, sometime next week. Okay. Okay, so this is the complexity measure. You can, Ramprasad gave a very explicit way to view this as the rank of a matrix. I won't do that because I don't know why, but I'm not going to. Okay, so what are the important facts about this? Right, the key thing is that it's subadditive, right? So if you have f plus g, is at most mu of f plus mu of g. Right, and this is because linear algebra is magical, right? If you have dimension is subadditive, this is dimension of vector spaces, partial derivatives, they're linear, so everything is just magical. Okay, so that's like the very basic thing. Right, what's the second lemma that Ramprasad also showed? Is suppose that you have a degree 1 polynomial, which I'm just not going to name at the moment. So you have some degree 1 polynomial, and you take it to the dth power. Right, what is the complexity measure of this polynomial? Well, suppose that you have f to the d. So f is here really degree 1. Well, what does the chain rule tell us, right? As Ramprasad did this morning, is if you take a derivative, say with respect to some variable xi, well, the d pops down, you get f to the d minus 1, and then you multiply by the partial derivative of f with respect to the variable xi. Okay, but the point is that if f is of degree 1, this thing is a constant. Okay, so this is in the field, in your field of scalars. Okay, and so what this is saying is that if f is degree 1, then any partial derivative of f to the d is some scalar times f to the d minus 1, as Ramprasad mentioned. And so the point is that if you want to do something like the derivative xi xj of f to the d, right, the whole point about derivatives is that they have this nice iterative nature, like compositional nature, that the derivative with respect to two variables is the same thing as the derivative of the derivative, right? Something from calculus, and you can do it formally. So this is equal to the derivative in xi of some alpha times f to the d minus 1. This alpha doesn't really matter, so you can sort of bring it out because derivatives are linear. And so then you get some alpha prime times f to the d minus 2, right? So what this is saying is that when you take derivatives, at every order of the kth order of derivatives, as Ramprasad again mentioned, you just have f to the d minus k, okay? And so how many possible types of derivatives can you get? Well, the point is that these scalars don't really matter because you're taking dimension, and so this is going to be at most, and in fact, equal to d plus 1. Okay. And so what does that mean? Well, that means that, in particular, because of subadditivity, the measure mu of our depth 3 powering circuit is at most s times d plus 1. Right, because each individual power of a linear form is d plus 1. You have s of them, and that's why it's this. And that's why I did this weird thing. I defined the size this way, so that the measure is at most the size. But that's sort of a cheat. Okay. So we have the measure that way. And then this key point here these are the building blocks, right? And then subadditivity. What's the hard polynomial? The hard polynomial is this monomial, right? And this measure is 2 to the n. Let me just do it again by example, right? If you take the partial derivative space of, say, xy, right, what is that going to be? Well, if you take the derivative with respect to no variables, you just get xy. If you take the derivative with respect to x, you get y. If you take the derivative with respect to y, you get x. If you take the derivative with respect to both variables, you get 1, right? So 2 squared is equal to 4, so that's a proof. Okay. Right, and so if you combine these facts, you want to get their lower bound, right? So suppose that x1 xn is equal to, a form of this, something of this form, right? Then you take the measure of both sides, right? The measures should be equal because these are the same polynomial, right? This should be at least 2 to the n, and this should be at least s to the times t plus 1. Okay, and then you put it all together and you get the result. Okay, so I'm belaboring this point because I want to emphasize how you can basically, not directly, but heavily use this lower bound to get a structural result, and then from that structural result you get your identity testing algorithm. Okay. So to get the structural result, there'll be sort of 2 ideas that are going to be involved here. The first idea is to sort of say we want to scale down this lower bound in the sense that what we really want to know is you're given a depth repowering circuit formula, and you want to know, is it 0 or not? Okay. What this lower bound is telling you is that if you have a small depth repowering, it is not a large monomial. That's one way of phrasing it. Okay. So we want to scale down. Okay, so suppose that you have a depth repowering circuit, and suppose that equals to some monomial where all of these variables are distinct. Right? Just hypothetically. Okay? So you have k distinct variables, it's a product, and they equal to this. I want to say, well, what does this lower bound tell us? Well, it doesn't necessarily tell us, I already promised you it's a monomial, so you sort of know it's not 0. But I want to say, well, it tells us something about k, right? This should imply that k is at most order log s, where s is sort of the size or whatever. Okay, and that's because if it was bigger, it would violate our lower bound. Okay, so we scaled it down and we got some non-trivial information about this sort of thing. So that seems okay, something. Now we want to make it robust, in the sense that I want to say that not only is this not a monomial on many variables, it's not even like close in some sense, not quite the limiting sense as Katan is asking about, but something else. Okay, so how am I going to make this precise? Consider the following. Right, if you think about Taylor series, there's some idea that in Taylor series, like there are sort of leading terms in some way, saying that because Taylor series is sort of some infinite approximation. I want to do something similar, where you do the following. F is going to be some monomial where this is non-zero plus lower order terms. Okay, so you have some monomial here, and then you have lower order terms. Now the difficulty is that what does it mean to have lower order terms? I want to order monomials lexicographically. Okay, so lexicographically means that you sort of the usual dictionary order. You sort of look at the first variable, you sort monomials by the first variable, so it's the highest thing is first, and then you break ties by the second variable, and then you break ties of ties by the third variable, and so on. Okay, this gives you a unique order on monomials, and this total order, and then that gives you a leading monomial. So this thing here is the leading monomial. Okay. And I want to say that the structural result here will be about the structure of this leading monomial. Okay. So the theorem here that I want to show for you, 13a or whatever, is that the number of variables in the leading monomial of one of these depth repowering circuits is order log s. Okay. So I can't say anything in general about the lower order terms, but this leading monomial has few variables. Okay, so it's the same thing sort of is going on here. If I promised you there were no lower order terms, I could just immediately appeal to this black box and get this result. What I'm saying is that this lower bound is robust. You can ignore lower order term, and the lower bound still goes through. Okay, so let me sketch this for you. Okay, the key lemma here is the following. I have this measure mu, okay, and I want to relate mu of f to mu of the leading monomial. In the sense that I want to say that mu is robust or ignores lower order terms. Okay, so the lemma here is that mu that I defined over there is the mu of f is at least mu of the leading monomial of f. Okay, and so what is the proof of this? I'm just going to do it by a sketch. So suppose that you had f is xy plus y squared plus 1. Okay, what is the leading monomial here? I want to say that xy is the leading monomial because I'm defining x to be the first variable and y to be the second. Okay, so if you sort these things, x is the first thing, so xy comes first because xy has more x than everything else. Okay, so then if you take the derivative with respect to x, right, what do you get? Well, everything else is killed here. This gets y. If you take the derivative with respect to y, you get x plus 2y. If you take the derivative with respect to both, you get 1. Okay, and the reason I chose this example is because let's look at the leading monomials of the derivatives. It's easy to see that the leading monomials of the derivatives are the derivatives of the leading monomial. Right? The example I had over there, the derivatives of xy are just exactly what I highlighted here, which are the same things as the leading monomials of the derivatives. Okay, so there's some sort of secondary lemma here, which is that the derivative, the leading monomial of a derivative of f is equal to the derivative of the leading monomial of f. Okay, yeah, okay, yeah, it was there. But if this is non-zero, okay. And using this lemma, you can basically say that the structure of these derivatives is basically like the structure of the leading monomials. And that way you get this lower bound. You have to do a little bit more, but the whole point was that we had this lemma over here, that the measure of this sort of monomial is 2 to the n. And the whole thing is, well, this is kind of as generic a monomial as you're going to get. You might have higher powers. This is multilinear. You might have higher powers, but it doesn't really matter. So what you can show is that the measure of a leading monomial is at least 2 to the number of variables in this leading monomial. Okay, and then you run through the claim, and you get the result. Okay, so basically by staring at this lower bound, and we scaled it down, made it robust, and we get the structural result saying the leading monomial involves 2 variables. But this is still a structural result. We need to use this to get identity testing. So let me now sketch that for you on a fresh board where you can actually read it. Okay, so the idea here is that we have this computation, and we know that the leading monomial involves 2 variables. What we want to do is we want to say, well, we don't know which variables those are. So what we want to do is we want to guess them, which will be hopefully not too expensive, and then we want to reduce to a polynomial with few variables. Okay, so the corollary here is that we want to get a polynomial in n d the log as d plus 1 size hitting set for this class, right? And so what are we doing? Well, we know that the leading monomial, if f is non-zero, right? We're assuming we want to hit non-zero polynomials. We're never going to hit 0 polynomials. F is non-zero, there's some leading monomial. This leading monomial has order log sd plus 1 many variables. But we don't know what they are. Okay, so step 1 is we're going to guess. We're going to guess these variables. And how many possible guesses are there? It's basically going to be n choose log s times d. Right? This is the number of possible guesses that we can have. And this, you can note, is quasi-polynomial. Right? It's n choose something which is logarithmic. Okay? And we can do, there's no issue in black box here. We can just we're just guessing stuff. The second step is we'll zero out out all other variables. Okay, and this is something that we can do in the black box because we're plugging in evaluations. What we're going to do is we're only going to plug in evaluations with non-zero parts within the set that we chose. Okay, so this is also black box compatible, but we need to make sure that this retains the non-zero-ness, right? And this is pretty clear because if I have this expression, I have f plus the leading monomial. If I zero out things not in the zero monomial, I might kill off lower order terms, but this thing is not going to be touched. And there's not going to be any collisions. Okay? So by zeroing things outside of this monomial, I haven't induced anything non-zero-ness, so this will preserve non-zero-ness. Okay? So what do I have in step 3? Well, I guessed this many variables. I set everything else to 0. So now I have a non-zero polynomial on how many variables? It's only going to be on log SD many variables. Okay? And now I can do this very stupid thing that I had from before, which is just do a brute force hitting set. Okay? So I'm just going to use a brute force. And what is the complexity of this? This will be d plus 1 to the log SD. Right? This is the degree bound I have, and this is the number of variables. Okay? And this is also quasi-polynomial, so I can also afford this. Okay. Okay, so just to recap, so I made you suffer and go through this lower bound for a second time. We stared at it, right? We scaled it down, we made it robust, we got the structural result. Using the structural result, we can then sort of isolate the structure, which is simple, and then hit that structure, and that gives us our hitting set. Okay, and there are better hitting sets. I won't talk about this one, but I will talk about this thing next in the next hour or 50 minutes, and this I'll talk about tomorrow morning. Okay, thanks. Okay. No, there might be other monomials. Right? So consider this, right? Like the leading monomial has 2 variables, right? But this has 1 variable, and if you zero out there's no other variables. So you have to do something non-trivial here to actually make that work.
They can have higher degree.
Yeah.
Also, they can have smaller support.
They can have smaller support or the lower degree, and it's wildness there. Yeah. Okay. All right, we'll come back in 4:10.